Hello everyone, welcome to this video. In this video, we'll be discussing about few examples which do not show isomorphisms, right? So let's see and move forward to our first example. In the first example, we are considering the group which is the set of all real numbers and the group operation is addition, right? So this is the group. Now we are saying the mapping phi from this group to the same group, right? This group of real numbers under addition. So the mapping here is defined like this. It is the cube of every element. So we are saying this is not an isomorphism. Let's see why this is not so. So we know because it is the mapping phi of x is x cube, so therefore it is 1 1 as well as onto, because for every element we can calculate the value of the cube root of x. So that means given some value b, right, we can always calculate phi of a such that phi of a is equal to b. Why? Because b is equal to a cube, and you can always calculate a from it by taking the cube root of b, which is always present in the set of real numbers, right? So there is no issue. This is onto. Similarly, it is also 1 1. We can prove that if we take phi of a as equal to phi of b, then we would have a cube is equal to b cube. So obviously from here we would have a cube minus b cube is equal to 0. So we can solve it further, and we may have a minus b. We can use the property of a cube minus b cube. So it is a minus b times a square plus ab plus b square is equal to 0. So that means a minus b is 0, or you have a square plus ab plus b square as equal to 0. So from this one you have a is equal to b, right? So from here we also have this 1 1 property. Now this phi is not operation preserving. Let's see how. Here we wanted to prove that phi of, if you take two elements x and y from the given group, then it should be equal to phi of x plus phi of y, right? So this is the property here. Now because phi of x plus y, what is this? This is x plus y whole cube, and you know this is not equal to x cube plus y cube because of the properties that we have learned about the cubes, right? So this x cube was basically your phi of x, and your y cube was your phi of y. So that means here we do not have phi of x plus y equal to phi of x plus phi of y. So therefore in this case we do not have an isomorphism from the group of real numbers under addition to the same group where the mapping is x cube, right? Moving forward to our next example. Here we consider the first group as the group of rational numbers under the operation of addition, and we consider the second group as the non-zero rational numbers with the operation of multiplication, right? With this thing over here we say G is not isomorphic to G bar. So this thing is not there. Why this is so? Let's see why. Suppose they are isomorphic to each other. So we say G is isomorphic to G bar. In that case, we would surely have some mapping phi. Let's call that mapping by the name phi, right? Which provide us with isomorphism. So that means this mapping would surely be 1 1. This would be onto, and this would also be operation preserving, right? If that is so, for this mapping we would say there would exist some rational number a such that we could write this as phi of a is equal to minus 1, because minus 1 is also another rational number. There is no issue in this one. We take this a from the set of this from this group G, right, where the operation is addition, and we have minus 1 which is present in the non-zero rational numbers group under multiplication. So therefore we may have phi of a is equal to minus 1. So we may write minus 1 as phi of a, that is this writing the same thing here. Now we may write a as half of a plus half of a. There is no issue. We are just manipulating and rewriting the sentences. Now because we are assuming that we have an isomorphism, so we also have operation preserving property with us. So therefore phi of A plus B, phi of this thing plus this thing would be equal to phi of this thing, the first thing, multiplied with the phi of the second thing, right? Because of the operations. The first operation is addition, so therefore we have the sign of plus here, and the second operation here is multiplication, so therefore we have the sign of multiplication here between these two entities, right? So that means you can write this as phi half A whole square. So that means you have written -1 as a square of some quantity, right? So this is not possible in real numbers, because in that case we would require the complex number. So therefore whatever we have assumed was incorrect. So we have assumed that they were isomorphic to each other. So this thing is not true in general. So therefore we have this as non-isomorphic groups to each other. So I hope you understood these examples well. I'll be talking about more examples in the next video. Keep watching.